Alright guys, I'm going to do number 25 from chapter 7. It says a small particle of mass m is pulled to the top of a frictionless half cylinder of radius r by a cord that passes over the top of the cylinder, as illustrated on figure 7.25. Assuming the particle moves at a constant speed, show that F equals mg cosine theta. B. By directly integrating, work equals the integral of the force times the dotted with the displacement. Find the work done in moving the particle at constant speed from the bottom to the top of the half cylinder. And this is the diagram. Alright, so let's get to it. Okay, so this is basically our setup, right? We have a cylinder. And there's a ball that we're rotating by applying a force F in this direction. So basically always tangent to its motion. Okay, so first let's find the component of its mass acting in the downward direction. So mg is the net force. Since we have this angle as theta, this angle would be 90 minus theta. And so this is theta, right? Now, since it's moving at a constant speed, the tangential part must the tangential part from the force must be canceling out the tangential part of its weight, right? So let's just say sum of forces tangential equals, so we'll call this direction positive, force minus mg. So this was cosine theta, right? Because this is theta. Cosine theta equals 0. Therefore, force equals mg cosine theta. So we've done the first part. Now it asks us to find the work done by integrating the work by... Okay. So this is our setup, right? We saw that again. I'm just going to sketch it out again because it looks kind of messy. Okay. So they're asking us to find the work done when moving the block from here all the way up till here. Okay. Now we've already shown that the force that's acting on it is equal to mg cosine theta, and the force is always acting in this direction, right? So now to find the work done in moving it up there, we just have to find the integral between the force and its displacement. Now over here, we don't know what displacement it's going under directly, but we know it must be related to its angle, right? And then we know that the radius of the cylinder, that's just r. So using the relationship that the arc length is equal to radius times the angle it makes, and taking the derivative of this, we get ds equals d r theta, and since r is just a constant, it just comes out, so r d theta. rearrange this. Oh, sorry, we don't need to rearrange this. Now this displacement is the same thing as the displacement it's undergoing when doing this work. So we'll put that up there. Work equals the integral of the force dotted with the displacement. And the displacement just becomes r d theta, where r is the radius of the circle. So r d theta. And now we're finding the sum from angle 0 degrees to pi over 2 degrees. So we'll put the limit of integration over there. Now we need to find how the force relates to this angle. So we found above that the force is mg cosine theta, right? So we put that here. Mg cosine theta dotted with r d theta. So now I'm going to take the mgr outside because they're just constants. Now this is a very familiar integral. Cosine theta is the derivative of sine theta. So if you take the integral, we get mgr times sine theta evaluated at pi over 2 minus 0. Now sine of pi over 2 is just 1, and sine of 0 is 0. So this will just simply come out to be equal to mgr. Okay, now just to confirm, this does make intuitive sense, because if this is the block, which has mass m, and this distance is r, the energy we're changing in this case is just the extra potential energy it gets, which should anyway be equal to mgr.